Greetings, everybody. This is a continuation of the videos going over the answers or solutions to the practice final. So now let's look at problem 3. It's a conservation of energy problem involving both translational kinetic energy, rotational kinetic energy, and potential energy. So what we have is we have an object of mass small m is attached to a string that's wound around a wooden sphere. Okay, and we know the mass little m. And then the sphere is mounted such that it rotates without friction on a fixed horizontal axle, and that axle passes through the cm of the sphere, meaning right through the center. Okay. Now, the wooden sphere can be modeled as a uniform solid sphere with radius large r given and mass large m, which is given. And now the mass is released, and the key here is from rest. And it's released when it's 6 meters above the floor. So you know your h. And in this problem, using conservation of energy, I want to find the speed v with which the object hits the floor. In other words, what is the speed v when it's fallen, when starting from rest, when it falls a distance of h? What is the speed v? Well, so here's the answer. Well, first thing is for the potential. Now remember, the potential energy of little m, the falling mass, its potential energy is changing because its height changes. So as I indicate here, let's choose the final position of the falling mass as our reference point for potential energy. Remember, reference point only refers to potential energy. By definition, we are saying that is the point where the PE is 0. And I should, let me go back with it. Reference point only refers to gravitational potential energy. You should all know that by now. And we are choosing the point where we say the gravitational potential energy is 0 and choose it as such. Okay, well now remember, this problem states use conservation of energy. Just like problem 3 on the final, you're going to use conservation of energy. You can use rotational kinematics, but I want to give everybody time to finish the final in the 3-hour window. And the conservation of energy method is a little bit quicker, and I think somewhat easier. Okay? And again, so we know large R, we know big M, we know little m, we know h. Well, let's apply conservation of energy. Well, that means the initial potential energy of the system is equal to the final kinetic energy of the system, where again the system consists of the falling mass and the rotating uniform solid sphere. Now, because the mass is released from rest, neither the sphere nor the mass has any initial kinetic energy, be it rotational or linear. They're not moving. So the initial Ke is 0. Then, after the mass falls a distance of h, it is moving with a linear speed v, and the sphere is rotating with an angular speed omega. So step 1, conservate PE initial equals Ke final, where the Ke final again includes the linear kinetic energy of the falling mass moving with v, and the rotational kinetic energy of the rotating sphere, rotating uniform solid sphere. Remember, it's pivoted about an axis right through its cm. So it's rotating about an axis right through its center. So PE initial is little m gh. Remember, the final potential energy of the falling mass. We're setting that to be our reference point. So the initial PE is mgh. Now the final kinetic energy, well, 1/2 I omega squared, that's the rotational kinetic energy of the sphere, and then 1/2 little mv squared, that's the linear kinetic energy of the falling mass. Now remember, uniform solid sphere. We're modeling the wooden the wooden sphere as a uniform solid sphere. Radius large r, mass large m. Let me pause it for a second. Alrighty. Well, what is the moment of inertia of a uniform solid sphere pivoted about an axis passing through the CM? What is I? Well, it's 2/5 in the parentheses. Notice the next line. MGH equals the 1/2 and the 1/2. Then what is I? Well, I is now the term in parentheses. 2/5 big M R squared. Why? Well, remember, it was posted in the second lecture notes from chapter 10. Just look it up. Uniform solid sphere pivoted about an axis that passes through the CM. ICM is 2/5 MR squared. Okay, so that's my 1/2 I omega squared. Then 1/2 little mv squared. Now we want to solve for v or v squared. I want to know, find the speed v, which would, or v squared. I don't really care. But notice, so now let's look at this equation. Again, the algebra is not complicated. The next step is the 1/2 I omega squared term. It becomes that. Then go to the next line. You get, for the going left to right, you get MGH. Then you get 1/5 big M R squared omega squared plus 1. Oh, Emily, watch out, buddy. That's my little kitten. He just jumped on the computer. No, stay down there, little guy. I got to finish this. No, get away. Hold on. I got to get rid of this cat. No, I guess got to move him in the other room for a second. Okay, I think he's gone. So the next line, so here I put in the moment of inertia for the uniform solid sphere. Then the next term, nothing complicated. You get MGH equals 1/5 big M R squared omega squared plus 1/2 MV squared. Now, in the next step, we need to replace omega squared with v squared over r squared. Remember, in general, for the relationship between linear speed v and angular speed omega, v is r omega, or equivalently omega is v over r. And I need to get rid of omega squared. I need to write it in terms of v. So omega squared is just v squared over large r squared. Put that in. Obviously the algebra is not complicated. The r squared terms cancel. You get this next line. Okay. And just don't confuse big M and little m. You want to be careful. Then you have this expression here, and you can just solve it for v squared. The algebra is not complicated, and you can leave it like this: v squared equals mgh over 1/5 big M plus 1/2 little m. And I like to clear the fractions, so I just multiply top and bottom by 10 to get rid of the 1/5 and the 1/2. But you don't have to do that. The numbers are going to come out the same. But that's your expression for v squared, and you get 93.2 meters squared per second squared, which gives you a speed of 9.65 meters per second. So conservation of energy, very, very easy. Now for the last problem, this is a problem where you have to, an object is undergoing an inelastic collision, and what's going on is you have this uniform solid sphere, and it's sliding without rolling on a frictionless table. There's a small lip at the edge of the table. When the sphere hits that lip, it then begins to rotate right there, about that rotation point. And I want to find an expression for the minimum speed v, such that when the sphere hits that lip and begins to rotate, it just barely, it just tips over and then falls off the edge of the table. By the minimum speed v, I mean just the minimum speed, it hits that lip, begins to rotate, and it just hits the tipping point, and then it's going to fall off the edge of the table. And we had a problem like this on exam 4. Let me pause this for a second. Or no, I don't think I have to pause it. Yeah, we had a problem similar to this on exam 4, where it was this cube. and you shoot a bullet into it, and then the bullet causes the bullet hits the sphere and causes the sphere to rotate about the line in the figure AB. Yeah, see in the problem, the cube is constrained to rotate about the fixed axis AB. So when the bullet hit, did I say cube? It's not a sphere. The bullet hits the cube is constrained to rotate about axis AB. So what happens is the cube begins to rotate after the bullet hits it. It rotates about that axis. And again, we want to know what is the minimum speed v such that the cube lands, when it lands on face, A, B, C, D, lands on that face there. Yeah. So this is a very similar problem. All right, so let's go back to it. Okay, so it's a uniform solid sphere. Well, a couple of hints. You need to use the parallel axis theorem to get the moment of inertia of a solid sphere about an axis tangent to the sphere, because it's rotating about this axis indicated by that black dot right there. Okay. And then this is what a lot of you didn't do on exam 4. Well, not a lot, but more than a few. Several of you didn't do this on exam 4. You have to solve this problem. You have to apply here in step 2. You have to apply conservation of angular momentum immediately before and immediately after the collision, and you also have to apply conservation of energy after the collision. You have to apply both of those, otherwise you cannot solve the problem correctly. And several of you did not do that. I don't know if you just didn't read the hint or whatever. Okay, so, well, first let's look at hint 1. Let's use the parallel axis theorem, because now once the sphere hits the lip, it's rotating about that point right there, that black dot. Well, remember, I is parallel axis theorem. I is ICM plus MD squared, where D is the distance between, why we call it the parallel axis theorem. It's the distance between the axis through the CM and the new rotation axis. Well, clearly that distance is R. So I is equal to ICM plus MD squared. Well, ICM, remember, it's a solid sphere. 2/5 mr squared, md squared, well, d is r. R is the distance between the two axes. Clearly that distance is r, the distance from that point to the center of the sphere. Okay, so you get 2/5 mr squared plus mr squared, you get 7/5 mr squared, that's our I. Now here, let's apply conservation of angular momentum immediately before and immediately after the collision. Well, immediately before the collision, we treat the sphere, it's a uniform solid sphere, we treat it as if all its mass is centered right at the CM, and the CM is moving with a speed of v. Well, remember, the distance from v to the rotation axis, to that black dot, that distance you can see from the left panel, that distance is r minus h. The distance between the line of the velocity, in other words, this arrow indicated v, the distance from the line of velocity v to the rotation axis, well, that distance is clearly r minus h. That shouldn't be very complicated to see. So the initial angular momentum is the mass. Large m is the mass of the sphere, v is the speed, and what we call the perpendicular distance between the line of velocity and the rotation axis, well, that distance is r minus h. Now, immediately after the collision, in the second panel, the uniform solid sphere is beginning to rotate with some angular speed omega. That's immediately after the collision. Well, L final is I omega. And what is I? Well, we know I is, by the parallel axis theorem, 7/5 mr squared. So you set these two equal. No, I mean, they are equal. They don't set them equal. Li equals Lf. So you get this equation. Mv parentheses r minus h equals 7/5 mr squared omega. Now remember, the rubric is when you apply Li equals Lf, conservation of angular momentum, you solve the angular momentum equation for v. not for omega. It's much easier. A lot of you, again, in exam 4, solved it for omega and not v, which is ridiculous. And you're making the problem harder than it needs to be. So solve the angular momentum equation for v. Nothing complicated. That gives you equation 1. V is 7/5, then r squared over r minus h times omega. Now, remember, we need to apply conservation of energy immediately before the collision. I'm sorry, I misspoke. Scratch that. Then you apply conservation of energy after the collision. Okay, so from panel 2 to panel 3. Okay. Well, so after the collision, at the instant when the sphere hits that lip and is just beginning to rotate, well, relative to the table, the cm of the sphere is at a height of large r. So it has an initial potential energy, and it's when it after the collision, right at the instant after it hits the lip, the cm is at a height of r, large r, and it's rotating with an angular speed omega. So the initial potential energy right after the collision is mgr. The initial kinetic energy is 1/2 I omega squared. Now, at the tipping point, remember we want the minimum speed such that the sphere just tips over and falls to the floor. Well, at the tipping point, omega is 0. It like teeters there for like a millisecond, then falls over. So at that point, the cm of the sphere is now at a height of r plus h above the table. Just look at the diagram. It shouldn't be that hard. So the final potential energy is mg parentheses r plus h. Now remember, you again, with conservation of angular momentum, you get equation 1. You solve the angular momentum equation for v. Well, obviously you're going to solve the conservation of energy equation for omega. So let's go ahead. PE initial plus KE initial equals PE final. MGR plus 1/2 I omega squared equals MG parentheses R plus H. Well, what is I? Next line. Well, we know I is the 7/5 MR squared. So put that in for I, omega squared, then MGRH. Then, simplify, and you get this equation here. And now you want to solve this equation for omega. Okay, so do the algebra, and you end up with equation 2. Omega is given by this expression. 1 over r, then under the radical 10/7 gh. Now remember, you take this expression for omega, put equation 2 into equation 1, and then solve for v. Well, I've rewritten equation 1 right here. And notice the omega is in the purple. Then I go ahead, and what is omega? Well, this omega, that's given by equation 2. So next line, right here. Then do the algebra, but now at this point just simplify it. And this simplifies to this expression for v. R over r minus h, then radical 14/5 gh. Technically the above equation is correct, but 70 over 25 can be simplified. And that's it. Now here is a good, I'll let you work through think about this solution. What if instead of a uniform solid sphere, what if the object instead was a uniform hollow cylinder with mass m and radius large r? Well, just the only thing that changes is the moment of inertia. You go to your table right here, hollow cylinder, mass m, radius large r. The ICM is mr squared. But remember, you have to use the parallel axis theorem. But it's worked out, but I'll let you work through that on your own. So that's it. I'll get these videos posted, and, again, let me know if you have any questions. But again, the think about this solution, I won't go over it. You should all be able to figure it out on your own. All right. Oh, the think about this solution is here. It's worked out. But you all should be able to figure it out on your own. But the rubric doesn't change. Apply conservation of angular momentum immediately before and immediately after, solve that equation for V, then apply conservation of energy after the collision from when the in this case the hollow cylinder hits the lip and begins to rotate, then it gets to the tipping point. Solve the energy equation for omega. You get what I call equation 2. Put equation 2 into equation 1, solve for V. The rubric never changes. If you don't do it the other way, the algebra is a lot more difficult. All right, let me get this posted, and good luck in the final.